Hi, welcome back. In today's video, we're going to be talking about trapezoids and kites. Now, unlike the last few videos when we spoke about a square, a rhombus, and a rectangle, we will not be talking about parallelograms or types of parallelograms. A trapezoid and a kite, I will get to here in a little bit, are not parallelograms. They have their own set of categories within the quadrilateral. They're still four-sided polygons, but they are not parallelograms. So let's begin with trapezoids. We will be talking about several types of trapezoids or different aspects of a trapezoid. We'll start with the most basic trapezoid. You will know that you're seeing a trapezoid when you recognize that there's only one pair of parallel lines. Notice how this line and the line below it are both parallel, hence these arrows. And because we have one set of parallel lines, the other two lines, regardless of how you see it, will always, if you stretch it, they will eventually intersect or trap. Hence the name, trapezoids. You can draw this very similarly like this, where it's centered more in the middle, where those are parallel. Notice how the non-parallel lines will eventually trap and create some sort of triangle. And this could be drawn in all kinds of ways. Parallel lines, non-parallel lines can be extended and will eventually intersect. That's how you can tell that you're looking at a trapezoid. Now, one of the first properties we're going to be talking about is that the angles between the parallel lines are supplementary. If I'm looking at this angle and this angle, they are consecutive and they are between the parallel lines. Those two will add up to 180 degrees. Similarly, I can look at these other angles. They are consecutive and they are between the parallel lines. Therefore, these angles are also adding up to 180 degrees. So as you can see here in the first scenario, we're trying to find the measure of angle K and angle M. So I know that these two angles add up to 180 and these two angles add up to 180 because those are the consecutive angles between the parallel lines. So let's start with angle K. I know that angle K plus 51 should equal 180. When I solve for angle K, I get angle K will equal to 129. Now, similarly, I can do angle J. I know that angle J, which is 87 degrees, plus angle M should also equal to 180 degrees. And when I move 87 on both to the other side, to isolate angle M, I get 180 minus 87. Which is 93 degrees. Notice how the summation of these four angles will still add up to 360 degrees because it's a quadrilateral. In this next example on the right, as you can see, we're looking for the measure of angle R. Now, R and Q lie between the sets of parallel lines. These are my parallel lines, and because they are consecutive or next to each other, I know that together they will add up to 180 degrees. And that's how I set up my equation. 12x plus 3 plus 7x minus 13 will equal 180 degrees. And now I can isolate the variable. 12 plus 7, when I combine like terms, will give me 19x. 3 minus 13 will give me negative 10. And that equals 180 degrees. As I isolate for the variable, I get 19x equals 190. When I divide both by 19, I see that x equals 10. Now, once I know the value of x, I can plug it back in to solve for the measure of angle R. So I go to R and I plug it in for x. So I have 7 times 10 minus 13. 7 times 10 is 70. And 70 minus 13 is 57 degrees. And this is how you find any angle really in a general type of trapezoid. Two consecutive angles will add up to 180 degrees. Now, there is a particular type of trapezoid that is called an isosceles trapezoid. If you remember back to when we spoke about isosceles triangle, an isosceles triangle is a triangle that has two congruent sides. Again, if you extend the non-parallel lines, notice how together they form a triangle. The two legs that are congruent are the ones that are side by side. Same thing with the trapezoid. Those two sides are going to be congruent. You can think of this as an isosceles triangle property. If I think back to isosceles triangles, I also know that the base angles are congruent. So these two angles will be congruent. And at the same time, the top two angles will be congruent as well, while keeping the properties of a trapezoid. As we spoke about earlier, any two angles that are side by side between the parallel lines are also supplementary. The other thing that we want to add here is that the diagonals between the vertices, if I insert a diagonal here, the distance from W to U will be the same as the distance from T to V. Since the legs are congruent and the angles are congruent, the diagonals across will also be the same distance. So let's put an isosceles trapezoid to use. As you can see here, we are given, and we are told that this is an isosceles trapezoid. The only way you want to assume that the picture is an isosceles trapezoid is if you are directly told, or if you see these two tick marks here on the side. Or maybe you're told that angle P measures angle O. You're being told a property of it by symbols or by words, and that's how you can start making these deductions. So, in this first scenario, I have MP, which is this side, is measuring 16x minus 10. I also know that NO measures 9x plus 8. Let's start with that component. I want to be able to solve for the value of x. I know that those two legs are congruent because those are the congruent sides of an isosceles trapezoid. So that I know that 16x minus 10 must equal 9x plus 8. And then I can solve for x. Move 9x to the other side. 16 minus 9 is 7x minus 10. I actually wrote this number wrong. I just realized that instead of a 10, it's supposed to be a 13 from here. Therefore, when I copy this over, it changes the value a little bit. So when I move the 13 over, I get 7x equals 21. And then when I divide both by 7, x equals 3. Now, as for y, I'm being told that Pn, that length, measures 5y plus 19. So that's this distance, 5y plus 19. I'm also told that MO, which is the other diagonal, is 12y minus 37. The isosceles trapezoid has diagonals that are congruent, very much like the rectangle and the square. Now, since their diagonals are the same, I'm going to set up a very similar equation. 5y plus 19 will equal 12y minus 37. I can move the 5y over to combine like terms. 19 equals 12 minus 5 is 7y minus 37. when I move the 37 over, 7y equals 56. Divide both by 7, and I'm left with just y equals 8. Now, if I wanted to find the length of any of these sides or diagonals, I would just plug x and y back into our expression. Here I have a few more properties of an isosceles trapezoid for two different scenarios. I want to find missing angles. Now, the thing that you want to identify is how the angles are related to each other. In this first scenario, notice how these two sides are the non-parallel, so these are congruent, which then implies the angle opposite to that side and the angle opposite to the other side will be congruent. Those are called the base angles. Therefore, my equation will be 2x plus 27 will equal 5x minus 12. And now I can solve for x. Move the 2x over. 27 equals 3x minus 12. Isolate the variable by moving the 12 over. 39 equals 3x. When I divide by 3 on all sides, I get x equals 13. Now that I solved for x, my interest is to solve for every single angle in this trapezoid. Technically, I only have to find it for 2 of them, and here's why. When I first plug in 13 into this side for angle D, I'm going to have 2 times 13 plus 27. 2 times 13 is 26. When I add 27 to that, I'm going to get 53 degrees. This measurement is 53 degrees. So angle D is 53. Since the two base angles are congruent, angle C is also 53 degrees. Now to find the angles that are left over, I also know, I'll do this in orange, that angle A and angle D are side by side between the parallel lines. So those two angles will add up to 180 degrees, right? Angle A plus 53 degrees should equal 180. So when I solve for angle A and I move 53 over, the measure of angle A will equal 180 minus 53. And that's 127 degrees. Now, since angle A and angle B are also congruent, that means that they're both 127 degrees. You could always check your work and add up all these 4 angles and see how they add up to 360 degrees. All right, this next scenario, we have an isosceles trapezoid as well. This is very similar to what we just did, but now we're given two different angles. I'm given angle J and I'm given angle M. Notice how these are not the base angles. Instead, these are the angles that are between the parallel lines, which means that together they are supplementary. So 10x minus 33 plus 4x minus plus 17 should add up to 180 degrees. In the previous example on the left, the base angles were congruent, so we made them equal. Here, the equation changes. They are supplementary because they are consecutive, and they are between the parallel lines. And now that I have my equation, I can solve. When I combine the x's, I get 14x. When I combine the other numbers, I'm going to be left with 16. 33 minus 17 is 16. Now when I move the 16 over, 14x equals 196. Dividing both sides by 14, I get 14. Now that I have my angle, my variable, I can plug it in, and I can solve for what I'm looking for, the angles. So angle M, all I have to do is plug it in there. I have 4 times 14 plus 17. 4 times 14 is 56, and when I add 17, I get 73 degrees. So angle M is 73. As we said earlier, the base angles are congruent. So angle L is also 73. I can plug 14 into the other angle, angle J, and I know that J and K will have the same measurement because those are congruent. I could easily flip my computer or my screen upside down, and you would see how those two would also be like the base angles. So I'm going to plug it in into 10x minus 33. So 10 times 14 minus 33. 10 times 14 is 140. When I subtract 33, I get 107 degrees. And that is a measure here and here. So as long as you can identify which angles are consecutive, which means they're supplementary, and which angles are going to be the base angles, which are congruent, you'll be able to decide how to write your equation. When do I make them equal, and when do I add them to 180 degrees? Let's talk about the last property of a trapezoid. In this last property, we're going to be talking about the mid-segment of a trapezoid, or the median. When we talk about this, we're going to be describing a new segment. We're going to insert a new segment in here that goes right in the middle of our trapezoid. From here to here. So no matter if you have an isosceles trapezoid or just a regular trapezoid, the mid-segment will be known as the median of the two parallel lines. It'll be parallel to the other two. And the property that it shares is very particular, is that that segment that I just drew will be the average of the other parallel lines. So let's say that I label this as segment A, B, C, D, and then this one in the middle, we'll call it E and F. Similar over here, I have A, B, C, D, and then the new segment, EF. So the way that this is going to work is I'm going to take the length of the parallel lines on the outside. A, B, and CD. If I know those lengths, the top and the bottom parallel lines, the original ones, I'm going to add them together. The length of AB plus the length of CD. When I divide it by 2, I will get the end result, or the length of EF. And you can think of it as this way, right? If I know the distance of A to B and the distance of C to D, notice how EF, the line in the middle, is going to land somewhere between the two other lengths. And it actually lands exactly in the middle. It's going to be the average of the other two lengths. So we're going to use this general formula to solve for any of those three different segments. And again, as you can tell by the name mid-segment, it's called a mid-segment because it's in the middle, which means this length matches this length, and this distance matches this distance. And that goes the same here. So let's try a couple of examples. Here I'm told that EF is a mid-segment of trapezoid ABCD. So I'm going to insert this new line in the middle. Because it's in the middle, the mid-segment, I'm going to call this EF. And I'm going to label some things. Notice how here I'm given that AB is 14, so this length is 14 units. DC, his length is 26 units. I know the measure of EF. is going to be between those two values. So to find it, I'm going to say the sum of 14 plus 26 divided by 2 will equal the length of EF. And all I have to do is add them and divide it by 2. It's literally in the middle. It's the average. So 14 plus 26 is 40. Divided by 2 is the length of EF, so we have 20. Notice how 20 is 6 units above and 6 units below. It's exactly in the middle, hence the name mid-segment, a segment in the middle of the two distances. In this other scenario, we have another trapezoid where Y and Z are the midpoints of the legs. If those are the midpoints, then I know that this distance is equal to this distance. And Z is the midpoint of the other length, which is those two are congruent. All this says is that YZ is the mid-segment, or the median of the trapezoid. So when I set up my equation, I want to take the 2 on the outside, and those are the ones I'm going to add. So PQ plus SR divided by 2 will equal the length on the inside, the middle. 5x minus 19. I guess I'll just label it as YZ. Now that I have my equation, I'm going to add things. PQ is 38 plus the other distance, x plus 14, divided by 2 should equal the length on the inside, which is 5x minus 19. And now I can solve for x. This is just a general algebraic equation. To get rid of the fraction, I'm going to multiply both sides by 2. That cancels the denominator, leaving you with 38 plus x plus 14 will equal 2 times everything on the right, which means I have to distribute. 2 times 5x is 10x, and 2 times 19 is negative 38. Now that the fraction is gone, I can just combine like terms and isolate the variable. On the left side, I can combine the numbers 38 and 14, and that gives me 52 plus x equals 10x minus 38. As I move the x over, I see that I have 52 equals 9x minus 38. As I move the 38 to the other side, I see that I end up getting 90 equals 9x. Divide both by 9, x equals 10. Now, I want the length of YZ, which means I have to plug this into YZ to find the length of it. So we have 5 times 19, 5 times x, so 5 times 10 minus 19. I'm just plugging x back into the equation. 5 times 10 is 50. When I subtract 19, 50 minus 19 is 31, which is what I was looking for. As long as you know which two to add up, the lines on the parallel on the outside of the trapezoid, add them up divided by 2 gives you the length of the one on the inside or in the middle of the trapezoid. So here we have a few examples. I would recommend you to pause the video and try these on your own. The ones on the outside, so GH plus the outside, those are the ones we're going to add up. So 2x plus 11 plus 6x minus 1. When I add them and divide it by 2, I should get the length on the inside, 25. And then I get rid of the fraction and solve for x. Multiply both by 2. 2x plus 11 plus 6x minus 1 will equal to 50. Combine like terms, I get 8x. 11 minus 1 is 10, is equal to 50. Move the 10 over. 8x equals 40. When I divide both sides, x equals 5. Now I want to find the length of kj, so I plug x back into kj. So I have 6 times 5 minus 1. 30 minus 1 is 29. 29 is the length of kj. For this next trapezoid, UV is also the midpoint or the mid-segment, so I'm going to add the ones on the outside. X plus 7 plus 6x plus 5 divided by 2 should be the length on the inside, which is 8x minus 3. To get rid of the fraction, again, I multiply both sides by 2. I have to distribute over here because there's two terms. So I have x plus 7 plus 6x plus 5 will equal, let's distribute, 8x times 2 is 16x. Negative 3 times 2 is negative 6. Let's combine like terms. I have 7x plus 12 equals 16x minus 6. Move the variable to the same side. 12 equals 16 minus 7 is 9x minus 6. Move the 6 over. I'm left with 18 equals 9x. Therefore, x must equal to 2. Again, I'm interested in solving for the length UV, so I got to plug the 2 back in here for UV. So 8 times 2 minus 3. That's simply 16 minus 3 is 13 is the distance from U to V. That's it. Do you know which 2 to add and divide it by 2 to get the length of the middle? Let's move over to kites. So this is our last quadrilateral we're going to talk about in this unit of quadrilaterals. A kite, as you can see, has no parallel lines. So there's no sets of parallel lines. It still intersects to it still creates 360 degrees total interior angle sum. But what we're going to notice here is that it becomes a kite exactly when the diagonals intersect at 90 degrees. There's no parallel lines, and the diagonals intersect at 90 degrees. When that happens, we're going to have two pairs of consecutive congruent sides, which means this length is going to match this length, and this length is going to match this length. Now, as you can tell, you can sort of imagine there being a triangle on the top that is going to be flipped or reflected to match the triangle in the bottom. So, since we're really dealing with two triangles here that are just sort of a reflection of each other, you can see how this angle will match this angle. So there's only exactly one pair of opposite angles that are congruent. Only these here are going to be congruent. And because those are congruent and they're intersected here by 90 degrees, I can tell that this length, this measurement here that I'm drawing with 3 tick marks, will match this length as well. And I'll put 3 tick marks. This is the kite. We'll do a few examples where we find the measurement of an angles, and then a few of them where we find the length of the sides. And yes, this is a kite like the ones that you fly outside in spring. A kite is only able to fly when the diagonals intersect at 90 degrees. So you can draw. If you're taking notes, this is a really good time to doodle. So, let's find the lengths. Let's find the measure of the missing angles. Here I have angle A and angle C that are given. Angle B and D are not. I do know, though, that angle B and angle D will be congruent because I know these sides are intersecting at 90 degrees. So I can tell that they're the same amount. So let's create an equation. All angles still add up to 360 degrees, and I have two angles here that measure the same amount. So 85 plus 43 plus x should equal 360. As I combine like terms, 85 plus 43 is 128 degrees. X plus x is 2x, and that's still going to be a total of 360. As I move the numbers over to isolate the variable, I get 2x equals 132. $232. As I divide both sides by 2, I get x equals 116 degrees. Angle D measures 116, and angle B measures 116. On this other kite, I also am given two sets of information. What I want to be able to do is identify the diagonals that intersect at 90 degrees. You're going to notice that there are two sets of congruent angles, and they will always be located across from each other. Notice how these two lengths are congruent, and the other two are congruent. The angles that are congruent will always be between the two sets of lines that are the same length. Therefore, it'll always match. It'll always be these two. So I already know angle J is 82 degrees. Now that I have three angles and I'm missing just one, I can write my equation. I can say angle K plus 82 plus 82 plus 71 will equal 360. The reason why K does not match angle M below it is that if they did, we would have ourselves a parallelogram where opposite angles are congruent. But we don't. We have 82 plus 82 plus 71. That's equals to 235. So angle K plus 235 will equal to 360. To solve for what's missing, we isolate the variable, and I'm left with the measure of angle K is 360 minus 235, which is 125 degrees. Now let's solve for the missing sides. We've identified which pair of angles that are opposite are congruent. Now let's talk about how do I find a missing length. Okay, I'm going to label here. I know that the diagonals intersect at 90 degrees, so I'm going to label this as a 90 degree angle. I have WX measures 14 in length, so this distance is 14. WR, this distance, measures 8. I'm trying to find the length of RZ, this length. Now, I know that RZ is also going to be this length over here. Or I can also look at this backwards, right? I know that this angle, or this line down here, is also measuring 14. I'm going to label this RZ section X. Notice how we have a right triangle right here. And there are two sets of identicals, so you can look at the triangle on top or the triangle directly below it. We have a right triangle, which means to find a missing length, we can use Pythagorean theorem. We have 8 squared plus x squared equals 14 squared. And just as before, we can do a little basic math. 8 times 8 is 64, plus x squared should equal 14 times 14, which is 196. When I move the 64 over, x squared equals 196 minus 64, which is 132. Square root both sides, x equals the square root of 132. Which is approximately 11.5. And since this length is 11.5, that means that this length will also be 11.5. Because these two angles are congruent, that means that the two lengths between them will also be congruent. Let's check out this next one. AC is 38, so I have a full length. Again, this is a kite, so I know that this is going to intersect the 90 degrees. The full length is 38. ED, this measurement, is 41. I want to find the measurement of CD. I want to find this length. We'll call it X. Now, since the full length AC is 38, I can cut it into two equal parts. I can say 38 divided by 2, and that gives me 19. And now I can just focus on this right triangle. I'll highlight it. I cut the 38 in half because the diagonals are perpendicular and it bisects that line, making them both 19. So in this right triangle, as long as I can properly identify my hypotenuse, remember that the hypotenuse is always across from the 90-degree angle. That's my C value, right? When I'm doing my equation, a squared plus b squared equals c squared, with Pythagorean theorem, the hypotenuse, or the one across from the 90-degree angle, will always be C. And the other ones could be A and B if I like. Those can be interchangeable. So 41 squared plus 19 squared should equal C squared, or X squared. And now I can do some basic math. 41 squared is 1,681. 19 squared is 361. When I add those two together, 1681 plus 361 is 2042. I square root both sides, and I'm left with the square root of 2042. And they get approximately 45.2 as the length of CD. That's pretty much. We worked with different types or aspects of properties of a trapezoid. For a kite, we have a few properties of a kite where the diagonals are perpendicular. We have one set of opposite congruent angles. And that's a wrap for our unit of quadrilaterals. I hope this has helped. Please don't forget to subscribe if you haven't already. Go ahead and like the video. And as always, we'll calculate later.